Okay, good evening. Tonight, the topic is look at this to see that. No, it's not clickbait, but once they post it on YouTube, it might be. When we make observations using the technology that we have, we're always observing in what is known as the electromagnetic spectrum or electromagnetic radiation. And this may be something that's visible to the human eye physiology, as in you're looking at light, as in, we just call the light that we can see with our eyes light. But there's all sorts of different wavelengths of light that our eyes cannot see. And we create detectors to look at that stuff like infrared or ultraviolet or radio or X-ray or gamma, create all sorts of instruments for doing that kinds of stuff. And if we're looking at large areas and we want to take pictures of it, we'll create detectors, imager detectors that we call cameras. If we're looking at a single point source of energy, like we're judging the brightness of a single star, it'll just be a single sensor, a detector. So there are circumstances in technology where we can't create a sensor that will pick something up because that thing just doesn't put out enough energy or has no energy it's putting out. So we can't detect it because it doesn't have a charge. So we'll get into what we do when that occurs, but suffice it to say, as long as we're kind of pigeonholed into only detecting electromagnetic radiation or various spectra of light, we're kind of stuck with, well, if it won't create photons for us, there's no way for us to detect it. Except tonight we'll talk about indirect ways of detecting things. Or as I like to say, just ignore the astronomical object behind the curtain that we can't see through, and just continue looking only where the light is good. So the human eye, the physiologic limitations, our eyes are almost, you could say, tailored for having just the right amount of detection without being saturated. So if you could see in radio, like you can see in visual light, even when you're asleep, you'd be constantly bombarded because there's long wave radio that can penetrate your eyelids. If you were able to see in gamma, same sort of thing. X-rays, well, if you went outside, yeah, from the sun. But, we're good that, we can only see in a certain set of wavelengths. And down here in the lower left, I have the same target, the Orion Nebula, but it's seen in different wavelengths. So the first one, which is kind of a collage, it is radio amplitude wavelengths. Those are all those little black lines. And then behind it, they have a typical white light visual image of the Orion Nebula. So the pretty gaseous, dusty things there in the background, that was underlaid, so it's actually under the radio mapping. The second one is the Orion Nebula in infrared. And you can see through the dust clouds and see a lot more illumination than you can with visible light. And the next one over is the typical, we mix in some hydrogen alpha and color it nice and red, and it's kind of visual plus. So this is what we do to see what's not visible to the human eye, so long as it's producing photons that we can convert into voltage that we can then digitize and come away with information, come away with a signal or a picture. So detectors for the invisible. We've created all sorts of detectors, some of which look strangely different than others. So if you're thinking of an infrared camera, kind of like Helen has as an add-on to her mobile phone, it's small, it has a little aperture, and it can detect infrared and take pictures. So that's the size of the aperture you need to take pictures in the infrared portion of the spectrum. But if you go down to lower energy levels and longer wavelengths, you get what you have up here in the upper right. That's the VLA, the very long array. Those are giant electromagnetic radiation detectors called radio antennas. And because you have such a low amplitude signal, and because it's such a very long wavelength, you need big dishes to collect all that stuff. and then it goes through an amplifier and a detector, and you have a digital radio signal. But, we're also not only improving the sensors, we're also improving where we put them to get a better view on things. And you can see the James Webb Space Telescope there. And here's an improvement. What she's holding up is a demonstration example of the latest gigapixel detector for the Rubin telescope. If you note, it's not one giant detector. It's actually a couple of thousand individual detectors. So she's holding up a detector, and based upon the telescope's field of view, if you want to, you can put the moon, which is half a degree, in that field of view. So they're going to be looking at 1, 2, 3, between 3.5 and 4 degrees in horizontal and vertical sky. But then you got to ask yourself, well, why didn't they fill out more of the chips? Those gray spots in the corners, why didn't they put some chips in there? Well, remember, this goes into a round telescope, and you only have so much square area. Once you put the holder in there, they will hold it in place, that they can't really make it perfectly round because they're using essentially off-the-shelf, high-end industrial chips that they just bought a lot of them and hooked them all together. So you don't really get a round detector. So when they talk about what you can't see in one of these detectors, everywhere you see those horizontal and vertical lines, there are no pixels there. They can't detect. So when something happens to be right on top of one of those lines, they can't see it. They're blind by that. So the way they do that is they move the telescope a little bit in order to get the target they want to see onto a CCD chip, actually another CMOS, CMOS chip, for them to be able to actually image it. We've also changed from just using the chips as they are to putting fans on the chips to cool them down, because the heat of the electronics in the chip actually creates electromagnetic radiation noise in the infrared. So if you're trying to create an infrared detector and your chip is actually producing heat, that will restrict the minimum light level you can see. So we cool the chip. There are people out there using Peltiers and water cooling, but at the high scientific level, they will liquid nitrogen cool them, or in the case of the James Webb Space Telescope, it's liquid helium cooled and liquid nitrogen cooled and as a Peltier, and it recycles on itself. So, you've got to get it as close to absolute zero as possible to get rid of all of the electronic noise that's part of the actual electronics trying to give you the image.
Yeah, and a ship big like that is mostly used for surveys, so it's not like it sees detail right there in the image, a very big detail, but polices the sky like a larger piece at a time to get more data from, pointing a tiny little point. So you can observe a bunch of data that it goes invisible for the ones that just see a tiny little bit.
Yes, what they're looking for is the smallest, dimmest, furthest stars, and they're trying to do survey images. So they will, with their high sensitivity detector, take pictures and move the telescope across the sky over the course of the night and take a survey image. If in your survey image still picture, because they're all still pictures, you can stack them and correct them and adjust them, but individually they're still pictures. Let's say you took a picture of a field that's 4 degrees by 4 degrees. What are the odds on there being nebulas and galaxies and very bright nearby stars in that field of view? The probability is pretty much 1, because it's very low magnification imaging. So around the bright objects, they have to have cutouts of, I don't care if there's a dim star, it's too near that bright globular cluster. So therefore they can't see it. So there's some places they just can't image despite having these massive detectors that are very sensitive, that are liquid helium cooled. There's just limitations. Now, whenever you see them describing problems with like constellation satellites, they'll never tell you those architectural design limitations of such imaging chips. It's just, they're there. What can they do about them? Why even announce them to the world? It makes them look like they're less capable than they actually are, which is the reality they deal with on a regular basis. And by the way, if you happen to be a geostationary satellite, it just sits in the chip as long as you're pointing the same direction. And it's very bright because they have, football field sized solar panels. So as I was saying, we move our instruments to different places to get better visibility. So we know that there's certain wavelengths of electromagnetic radiation that will not penetrate the atmosphere of the Earth. We know that there are some wavelengths that get interference from other things here on Earth, like if you're trying to do radio astronomy, you don't want to be parked next to a downtown area where everybody's got their cell phone and their computers on. You want to go out into a mountainous area where you have a bowl range of mountains around you, and you sit down in the bowl where there's no electronics and there's no electromagnetic radiation coming in from adjacent places. In optical astronomy, you go where it's dark. So you go to mountaintops like Keck in Hawaii. You go to, if you want to put a large array in of radio antennas, you go to the Atacama High Desert in South America, and you can flatten off the top of a mountain peak at very high altitude, like 14,000 feet, and that's where you put your array, because you're not going to have any radio interference. It's very cold, and it's very dark there. Or you fly it above most of the Earth's atmosphere in an aircraft like Sophia, an infrared
It's
telescope.
always clear in the stratosphere.
It's always clear in the stratosphere, but not to certain radio wavelengths. It's always, if you've got any moisture in the sky, it's a block. But we also fly helium balloon observatories. Athros is a popular one. They actually launched this from Antarctica, and it circles the South Pole, taking images for a period of time. The last time it was over a month that it just hovered up there. They don't let it go up so high that the helium will pop the balloon. They let it go up to a certain level, and then they gradually reduce the helium pressure so it won't go up. It's counterbalanced and it won't go up any higher. So it just sits there and it goes around the polar currents at the South Pole and does astronomical imaging. And then they let the helium out and it lands and they can reuse it again. We still fire off suborbital sounding rockets. If we want to make a particular observation from an altitude like 70,000 feet, 80,000 feet, where airplanes aren't typically, there's a rocket that NASA uses called the Black Brant. I think they're at Black Brant 3 or 4 now. But they continue to fire those sounding rockets off of Wallops Island in Virginia. You have low Earth orbiting short-term observatories. You've heard of CubeSats, these little tiny satellites that they just sort of scatter out there, and they're so low in their orbital level that they encounter very large concentrations of air molecules in the upper atmosphere, and their orbit degrades within a month or so, and they fall back and burn up. Those are low Earth orbiting CubeSats. They have very short-term lifetimes. Then there are the ones that are more expensive that might be up there for a couple of years, but eventually even those fall back. There is an ultraviolet satellite called ROSAT that was up there for a few years, did some really great work, and came time for it to come tumbling down, and they just burnt it up over the ocean.
Monroe, what telescope is that in the picture? That's not the Hubble.
That's not the Hubble? What is that?
No. I don't remember that telescope, but it's not the Hubble.
Oh, okay. Well, we're about to get there. So there are long duration, low Earth orbiting telescopes, like the Hubble Space Telescope, which, by the way, this isn't. And then there are the much longer duration, kick it way out there, but not so far out there that we can't work with it, the Spitzer Space Telescope, Gaia, and the James Webb Space Telescope, they've all done these virtual orbits around L2 so they can have a certain amount of time there. And when their fuel runs out, then they put them into a solar trajectory orbit where eventually they go behind the sun, we lose contact with them. So Helen pointed out that it kind of looks like the Hubble Space Telescope, but it's not.
I built
Here's
many
the Hubble
models.
Space
Yeah.
Telescope.
I
So
know
does
my
that-
Hubble. I built many models of it.
So does that look more like the Hubble Space Telescope?
Yeah, that looks better.
Okay. How many people know what that is?
Is that the CIA kind of satellite?
That's exactly what it is. That's part of the Corona program. That is a KH-11 spy satellite.
Hmm.
And for those people that think, oh, NASA just got the prescription wrong when they put Hubble in orbit. You know, if you put in orbit something that always looks down, it's going to focus at a different focus depth than something that wants to look out to infinity. So that's a KH-11 spy satellite. We don't launch those anymore. We launch newer stuff that's still clandestine, so I can't find out about those. But rumor has it that the X-37B, the little space shuttle that the reconnaissance office owns, has something that they open up its cargo bay and they look out with it, because it's cheaper to just put telescopes like these in the cargo bay of the X-37B and then just put it up there for like a year at a time and change its orbit to go wherever trouble spots are, rather than sending up different short-term satellites. You just put one of those good telescopes in the back of the X-37B and have it go to where the trouble spot is, do what it does, and eventually it'll come back to Earth and we'll refuel it, put in a new instrument, next generation instrument, and we're back up there again. So I think that's where the reconnaissance office current program is. But yeah, that's a KH-11, and that's Hubble. Now, the first thing you can tell is that's Hubble because it says NASA on the bottom right there. Towards the front on the belly of it, it says NASA there in the worm logo. But the other thing, if you look closely, the butt end of Hubble, because it has so much electronics on board, the butt end of Hubble, that wide cylinder at the back, is just a little bit longer than a KH-11. So there's Hubble. There's a KH-11. Hubble's just a little bit longer in the butt. But other than that, to the average person, they're indistinguishable.
Yep.
Okay.
Only it's just distinguishable for me because I build models of the Hubble.
I know. I just thought that was, for entertainment value. I'd put that up there and see who noticed. I was expecting you to notice and nobody else would notice. But I did. Yes, I did that deliberately. So indirect detection of the directly invisible.
So I want to visit that. That looks
We watched
so
a program
cool.
on this. This is something called the Ice Cube Detector.
It's almost looking like Tatooine. Oh,
Yes,
I want
yes.
to use it.
Notice it's elevated above the ice because the ice level changes and you get snow drifts and things like that. It has the two basically entry columns on the ends, but the whole structure is designed for survivability at the South Pole. It's very close to the South Pole, not directly at the South Pole, but very close to the South Pole. And what they did was they drilled holes in the ice and then they lowered down a string of sensors. So you would have a string, it would have a sensor, a string of cabling, a sensor, a string of cabling, this sort of like pearls on a string. And they lowered that down into the holes that they melted into the ice. And the holes would fill up with water and the water would freeze over. So it's a self-sustaining grid. So they put a pattern of these strings down into the ice, a couple hundred meters. And that's the neutrino detection grid. Now they have no ability to detect neutrinos directly. but there is this thing called Cherenkov radiation. If you ever saw a picture of a fission reactor, that's that blue sort of toilet bowl water color that you see of the water. Is when the neutrons exit the core of the reactor, they'll emit photons, and when the photons encounter the water, which is much higher density than the air gap inside the fuel rods, it slows down. When you lose energy at that dramatic a difference, there's only one thing you can do, and that's give off a photon of light to compensate for it. So the photon of light it gives off is in a particular wavelength, which gives you that deep blue, almost violet color. That's not ultraviolet, it's just deep blue. And so that's called Cherenkov radiation. And that's what the ice cube looks for. It's not looking for light from a neutrino. It's looking for that deep blue little pink light, very short-lived, very specific wavelength. Somewhere in the block of ice, that's what they call it, the ice cube, a block of ice between all the detectors. So the detectors aren't in water. There are other observatories like this that are actually in pristine water in a sphere underneath the Atlantic Ocean. But this one is actually in ice. Now, it's very, very pure ice, so it's really clear, but given that ice has a different index of refraction than does water, it slows the photon down even further to produce Cherenkov radiation. So that's what they're looking for, is something they can't see, neutrinos. Now, why is it that they can't see neutrinos? Because neutrinos supposedly do not have any charge. So they're not like an electron. They don't have a charge. They're neutral. They're kind of like a neutron. So they don't interact with stuff. But when they do actually interact, they produce a photon, and when the photon slows down, you get light from it. So they can't detect the neutrino because it has no charge, which means directly no photon, which means no conversion to an electron, therefore no voltage to measure, therefore it's invisible. But if we look at something else that occurs because of an interaction, oh, we can look at that. That's visible. Think of a black hole. You can't image the black hole directly because all the electromagnetic radiation goes in and none of it comes out. But at the edge of the black hole, there's a lot of energetic interaction with the mass that's being pulled into the black hole, and therefore that will give out all sorts of things. It will give out infrared. It will give out radio. Most people don't realize that the image of the black hole is actually a radio telescope image that they mapped onto visible colors. But on the right there is a new kind of observatory that's being built. It looks very much different because it works at a particular wavelength. And the mirror off there to the right is very, very reflective, and it looks blue in color. That's because it's trying to reflect the Cherenkov radiation and concentrate it. So up in the atmosphere, where there are gamma rays, cosmic rays, they do interact with the Earth's atmosphere. And when they interact, they produce this really dim blue, short-lived light. And the Cherenkov telescope array will be an array of telescopes like this that are around the Earth that pick up Cherenkov radiation and attempt to image it. Now, why does the front, the actual secondary, look so weird? Because that's where the detector is. If you look at most large telescopes, the detector is not out at the secondary. That's a reflector. The detector's inside the Cassegrain hole. But if you're going to be detecting Cherenkov light, you don't want to give up any of it by having a secondary reflection. So the Cherenkov detector is actually in that little white box on the left at the front of the telescope where the secondary is. So you have to have this giant hoop holding the secondary in place. So that's one of the medium-sized Cherenkov radiation detector telescopes. And that's a bunch of international dignitaries cutting the ribbon on the first prototype being opened for observations. So if we want to look at things we can't see because our detectors can't detect them, we can look at what we can see with our detectors that are a side effect or indirect observation of things we can't see directly. So that's the whole point of this, is don't look where you can see to find something you can't see. Look where you can see to find an effect of something you can't see. And that's what this is. So Elaine brought this to my attention. And there was a research project. It was a joint project between the Subaru telescope in Hawaii and some astronomers down in Australia. And what they did was they said, there are some faint stars that are too faint between galaxies, but are at about the same distance as these galaxies. They're just stray stars. And they can't image them directly because they're too faint. But what if in infrared, we were to basically overexpose the image? Would we be able to see these stars that we cannot see otherwise? Turns out, yes. So they're taking the fog of infrared light that is between galaxies. So if you look at a galaxy, the galaxy is going to be bright. But as you saw with the Orion Nebula, when you go deep into infrared, you can see the fog of infrared light well beyond the normal visible diameter of the galaxy. Well, that fog of light can be picked up in infrared, and if you overexpose it, you can start to see stars, and you can judge their size and their mass and, chemistry parts of stars. But in order to see them at all, you have to look at them in infrared, but not their direct infrared. You look at them by the diffuse infrared background illuminating the area around them so you can detect them. So this is, observe what you can to look at something you can't observe. And this is a new and promising area of observing things that up until I'd say maybe 20 years ago, we never considered it. But now there's just all this research coming out of the woodwork, as they say, of I want to find something that I can't see. What is there that I can see that might be a secondary effect of what I can't see? So here's another one. And this one is still in the, we're looking to see if this has legs, as the saying goes. Indirect detection by distortion fields and frame dragging. So when an object goes across your field of view, it's going to be, occulting things. It's going to go in. If you have a dark object and it goes in front of a star, you'll be able to actually see the star wink out and then come back, and you can look really close at that star because you know where the object's path is after it crosses a couple of stars, and now you can follow that object, and you can't see the object itself because it's just too small and too dim, but it does cause the light from stars in the background to dim out and then come back. But that's not what we're looking for here. What we're looking for here is literally as a very dark object traverses a bright field, it creates a distortion in the field, in the actual electromagnetic radiation coming in. And it's not occulting it because it never completely obscures the star. It just goes by close enough that the basically the gravity of that object very minusculely bends the light of that star. And if you go back to when they were trying to prove out Einstein, and they were watching a total eclipse of the sun to see if starlight bent in the presence of the large gravity of the sun, they watched as when the sun was covered, you could then see where the star was versus where it normally is when it's not in the path of the sun. So the light from the star was being bent by the gravity field of the sun. And as the sun moved past, the starlight moved back to where it would normally be. So you've got these two things called distortions and frame dragging. And I sent an email off to Mr. Brown, who's looking for another planet, and said, have you guys tried looking at distortions and frame dragging? Because if there's another planet in our solar system that you're looking for is about the size of Neptune, it's going to have a significant enough gravity that even if you can't see it because it's too dark, even in infrared to see it, it will create a distortion field so that the background field of stars will slightly move as this thing goes in front of them. Now, it'll obviously occult some of them, but if it's small enough and dark enough, but still has a large mass, it can move the star's light around without actually covering over the star. It just sort of went into the black hole of the thousands of emails per day that he probably gets, but can't say that I didn't say it. So someday if we ever go, we found Planet 9. How did you find it? By watching it frame drag the background stars. You heard it here first. But I think that's a promising detection technique that is indirect. So what we've really got to do is remove the electromagnetic radiation blinders. We recently found out, because we've created different kinds of detectors of gravity waves, that much like radio has all different wavelengths, different frequencies, across the electromagnetic spectrum, you have radio and infrared and visible and ultraviolet and X-ray and gamma. You have different wavelengths. And you create a detector that can only see in a specific band, or you create a radio receiver that can only detect in a specific band. Well, when they created gravity wave detectors, they built LIGO and Virgo and places like that. And turns out they're only sensitive to gravity waves at a particular wavelength, at a particular frequency. Well, they're now building detectors for gravity waves that have different physical properties. They're not, 10-kilometer L-shaped things. They're much, much smaller, and they can pick up different wavelengths of gravity waves. And they found out that there's essentially, like there's a cosmic microwave background, there's a cosmic gravity wave background. So they're now starting to focus in on the new approach to detecting things in the sky is by, if we can observe indirectly things as the gravity wave detector sees them, we may see things that we cannot see that have been there all along, but because we're only looking in the electromagnetic spectrum, we never saw them. The proverbial rogue planets and black holes that are sort of zooming around all the time, if you don't know how to look for them, you never see them. But if we take a wide field gravity wave image of a certain part of the sky, because there's no star collisions or star formations going on, we're not going to see the normal wavelength of gravity waves. But if there's a background pattern there, we may actually see a background pattern of gravity waves being distorted by things moving through that field. So this is another, put a push pin in that and let's see what comes of it.
The other thing is that we can see stuff that is during the dark ages of the formation of the universe. So this is like a new window on the science. Like less than 10 years ago, this was only a theory, but that Albert Einstein postulated, and we took so long to actually prove that was actually working. It's not just errors or interference.
Yep.
And then from one year to the other, when we finally prove it, that's what actually observing, that people started from the woodworks using the equipment they had already, make little changes, widening the precision of the instrument, and then like it's the background gravity. So this is amazing, because remember that we kind of figure out that was the Big Bang, because we looked at the background, the microwave background radiation. We looked at the formation of galaxies because we looked at the infrared background radiation. And now we are observing something that was only, not even possible 10 years ago. And now we are looking at gravitational background. That's amazing. It's like a new window in the science that wasn't not even thought about it before unless mathematical proof.
But we're actually moving from electromagnetic radiation direct detection to gravity wave detection indirectly by electromagnetic radiation. So when the gravity wave is detected, we're detecting it through interferometers. So it's you've got a source of energy, and when the source of energy is affected by the gravity wave, you're not detecting the gravity wave, you're detecting its effect on the electromagnetic radiation that you either created or are looking for in the sky. So the thing you can see with the detector you have. The thing you can't see, you can indirectly see with the detector you have. Now, the stuff that's active, like neutron stars colliding and things like that, or type 1a supernova, that's the detectors over on the right. That's the initial ones, like the LIGO and the LISA kinds of things. Those are great for detecting the currently active stuff. So they're going to pick up, collapsing supernovas that are collapsing or, at their distance collapsed a million years ago. But they're not going to detect the cosmic gravity wave background from the Big Bang. That's going to be this fog of gravity waves. But I suppose that much like we didn't have radio until somebody found a way to modulate the electromagnetic spectrum, someday in the hopefully not too distant future, when we learn how to modulate light amplitude gravity waves, we may find that this stochastic background actually has a signal in it. So we just need to create the right kind of detector. It's kind of like if all your life you were using smoke signals for communication, and all of a sudden somebody handed you a radio receiver. And you're in modern times, so the amount of radio stuff that's going on is just, you never knew it was all there. Well, if we find out that there are folks out there that have been modulating gravity waves and gave up on direct modulation of the electromagnetic spectrum, we may find that there's a whole conversation out there that we were just never privy to because we can only detect electromagnetic radiation blinders on. My 2 cents worth for what it's worth. So stop looking only using light that is good. Look using something other than light, like gravity waves. And where do I get all this miraculous stuff? Well, obviously, there's some of it that's on the internet, but as Helen pointed out a couple of weeks ago, some of this stuff comes from news bureaus, and they may not actually have the correct image for the story that they've got. It was a pretty picture, and they just sort of stuck it in there. So one of the places I go to that actually has all of the raw data and the processed data is the Mikulski Archive for Space Telescopes, which is part of Johns Hopkins University. It's part of the Space Telescope Science Institute. So they have, whenever you want to say, where does NASA keep all this stuff? Well, NASA has active project stuff. They keep on project-related databases. And when they have specific endeavor fields like gamma or X-ray, they have a high-energy website that they keep there. But what about all the stuff that we observed from like 50 years ago? Where'd all that data go? It wound up here in this archive. So as they turn down Sophia's data, not just the pretty pictures, but all the raw, gory, detailed stuff winds up in this archive. So if you ever want to look at the good stuff, so to speak, this is the place to look for it. And in conclusion, you can only see what you see with however you are looking. So if you're only looking with your eyes, you'll only see what's visible to human eyes. If you want to capture other stuff, you've got to have sensors specific to capturing in that wavelength. So, radio antennas and receivers, infrared cameras, UV cameras, X-ray detectors, gamma. And if you have a detector that can't detect other stuff like neutrinos, maybe you go with the indirect detection. Indirect detection is becoming more of a recognized and valuable means of observing what you can't see with your instruments. And gamma galaxy group reflections in infrared, basically making invisible stars look visible, is just the latest thing. And thanks to Elaine for suggesting the research release. And I took that and made it into a presentation topic and fleshed it out from there. Not a huge number of slides, but it'll look good on YouTube, I think. And for those people that want to look at the inter-group light from the gamma galaxies at Subaru, there's a bunch of links there. And indirect detection of neutrinos in the atmospheric sky through Cherenkov radiation. There's a couple of the detectors there. And comments, questions?
One is first, shout out to the United States government that uses the public funded research and places in those repositories of data for everybody in the world to look at it, because not every university has enough money for, funding research in many places of the world. And having that repository of data gives the chance for people, doesn't matter if they're college or university, they can look at the data and do, their master degree, the doctor degree without even touching, any of the fancy telescopes, because the data is already there. And the other ways is the ingenuity of, you see all those instruments that Monroe gave the example, is that is something that is being used for the last 20 years that way. But comes engineer talking with a physicist during lunchtime, and what about if you could do this? What about if you could do that? And that becomes the new idea or the new use of that instrument. And for me, it's always like fascinating how we already have that data, we already have the instrument, but nobody before thought about how to use in a different way. And this is, for me, it's like how humanity progresses slowly because of those silly conversations in the lunchtime that end up being a new technology.
Well, when NASA was first being asked to put together a long-term, like forever kind of archive, questions like, what's the return on the investment? Well, now that you have all these projects where, hey, Hubble saw this 15 years ago, but nobody made a big deal about it because we weren't looking for it there. Or we weren't looking for that, we found this. They look where the light's good. Well, what about what you captured where the light wasn't so good? Well, we have computers nowadays that can pull out that information from what you didn't see before. So that's the return on investment. And you have other universities like Harvard that are digitizing all of the glass plates from back in the era of photographic grayscale observing, because they were sensitive enough to capture the positions and brightness of things before we ever had digital recording and could load stuff on the web on a server. So they are scanning that stuff and putting that into the archives for people to look at. Now, the archive at Space Telescope Science Institute, as Helen pointed out, is a place where if you know what you're looking for, you can find data sufficient to do your doctoral thesis without ever buying time on a current observatory. The data is already there. You're just doing new research with stored data. And anyone can do that. So if you have an interest in something that a telescope might have captured, you don't have to be a research fellow to gain access to that. You just have to, please provide me a login to the archive. I have a login to the archive. Didn't cost me anything. I didn't have to prove I'm a PhD, obviously. And I have access to the archive. Now, I can't obviously change the archive and have no intention to, but I can scan anything in the archive. But the cute part is, because I did the James Webb Space Telescope stuff, I don't have to wait a year for the James Webb Space Telescope data to be accessible to me, maybe a month. So it's still not yet publishable research when I can look at it, so I can grab an end result picture and include it in one of these presentations from the James Webb Space Telescope, something that the news media can't do because it's not an official public release yet. But I can't use the NASA logo or the NASA worm logo, the meatball of the worm logo. I cannot put those on the picture. I can just say, this is something the Webb telescope took a picture of. So sometimes there's boundaries on what you can and can't do with the data.
Unfortunately, for other sciences, that doesn't happen, because everything that's coming out for universities, like in biology or in chemistry, or everything is already so patent and so close data that the development is happening so slowly. At least in physics and astronomy, the development is becoming huge and it's everywhere. And it actually returns to the economy, because the changes that you do in CCD cameras end up in your phone, becoming like the technology developed for them becomes the CMOS on your phone camera, and microphones and other sensors, the miniaturization of those sensors that end up in your phone. And we're observing that, all the technology that's developed to put those space telescopes to do that esoteric research ends up in your everyday instruments. The computer that I'm speaking now have that technology. And unfortunately, like for other sciences, because if some kind of awesome innovation, they put in the drawer so it doesn't go out because it doesn't take their market, or if it does, it's so patent that even if you mention, you get sued out of existence, and you cannot publish anything scientific about that. So it is sad for some sciences and awesome for astronomy.
Think about it this way. If you want to do research in high energy physics, you need a collider. A collider is going to cost $1 billion.
Billions.
If you want a space telescope, it's going to cost you multiple $1 billion. That's something corporations cannot easily cover the cost of. They get the government to do it. But if you're doing chemistry, you're doing biology, those sciences are things that a private corporation can fund a university research project and get all of the data, and it becomes their data. The university is very happy to receive $1 million or $2 million to do a research project on a pharmaceutical, or on something in chemistry, or even in optical physics. They're okay with receiving a couple of $1 million to do that project, because the grad students have something to do. They can do a doctoral thesis in something that's going to be an up and coming technology, and they'll probably get a job at that company. The one that comes to mind is, if you remember back maybe 8 to 10 years ago, all of the drone technology that we have now, all of the autonomous drones, those were university projects that were funded by the companies that wanted to mass manufacture drones or surveillance. So they gave the universities money for the students to go off and create autonomous drone technology that then the companies put into products and charge money for it. And the data, the research data, becomes owned by those companies and will not be shared with other companies that might be their competitors. So if whatever you're doing costs many, many millions to billions of dollars, no problem. Everybody wants to have that public. But if it's something you can sequester away where only you get it, if it costs you a few $1 million, money well spent.
Yeah, I understand that.
Yep.
It's just like we have an example of the pandemic, where all the biology labs that were working on the vaccine, they opened their files, they share the files, and instead to take 10 years to develop the vaccine, it took a year. It was amazing.
Well,
of course, they had the base science that was developed before, but you have testing, you have all the stuff that it would at least take 3 years for developing like a flu vaccine with the technology that we have already. It went so fast because, of course, we have the sampling of disease people was higher, but you have also open up all the files and sharing the information, and this like brought the development very fast.
Yes, it did help, but what really helped was fast tracking the patient studies.
Yep.
Instead of it taking 5 years, it took less than a year. Documenting the research, not having to put out 600 pages of printed material that you physically hand to the FDA, doing it online allowed the FDA to do the analysis much faster. So the research and development actually was already in progress because coronaviruses have been a nemesis of the human population for a while now. But the particular variant of it, 19, as in 2019, that was new and different. But the avenues that they were looking at were held captive by corporations, and government action accelerated the final stages of getting those to market. And they continue to do that. But that's, when the environment's right, they don't mind doing what they need to do. But when the environment's profit rich, there's a different approach to doing it. Anything else?
Yes, it's very amazing that at least like it started with NASA, but now the European Space Agency does that too. Is that open up in the files and the data and the research? Because before they only spill out like open for people on the colleges and universities in their own countries, even though it was public data, they kept local. And with the example of NASA, all those files from all those countries, they're related to some sciences, are open for the perusal of anyone, and that brings innovation. That brings the technology that we have in our pockets today.
There's a different approach to spending government money for science. In the US, we like to do a lot of fanfare with it. We're going to announce so much funding was awarded to some large company to build some instrument or aircraft or rocket or whatever. So there's a lot of fanfare associated with it.
Yep.
If you go over to the German government and you look at their funding, they have an enormous number of programs and research institutes, and that is just actively funding all sorts of science, but they don't do a lot of promotion about it. Now, if they make a discovery, they will promote it. But the actual doing the research and getting the funding for the research, it's just a matter of the EU government saying, and we're going to spend money in this. Like we have a decadal survey where we say we think we ought to be spending money on the following things. They have a continual annual survey where they find, what they need to do research in. And it's not always going to produce like industrial revenues. Sometimes it just improves science because there's a belief that if we improve the science somewhere downstream, we'll get mobile phones. They don't have to directly see the line of evolution of the products. They can just know it's good to be doing this stuff, so they do it. But there's a lot of stuff that goes on over there. The DLR was one of the contributors to NASA's SOFIA program, not at a big level, and they certainly didn't have the funding to take it over. But that's not to say that they're not spending billions of dollars on astronomical research. That's just to say their money's already allocated to other things and they couldn't come up with the money that NASA wanted. Okay, I'm going to stop sharing. Anything anybody wants to say before I stop recording?
Time for BS.